Welcome back to this lecture on nested quantifiers. In this second segment, we're going to make sure we understand what it means to nest quantifiers by studying the truth conditions of such propositions. In other words, I'm going to consider any binary predicate P, and then I'm going to study every possible way of turning it into a proposition by quantifying it. So the first proposition we're going to consider is the double universal quantification for all x for all y, P of xy. Now, when is that proposition true? This proposition is true when the predicate P holds for every single pair of values for x and y. So here is the truth condition for this proposition. Now, when is this proposition false? Well, intuitively, it's false if it is possible to find at least one pair of values x and y for which P of xy is false. So let's write this down. This proposition is false if at least one pair xy makes P of xy false. Now, instead of coming up with this answer intuitively, another way would have been to consider the negation of this proposition, since this proposition is false when its negation is true. So let's write down the negation of this proposition, and let's transform it by moving the negation across both of the quantifiers and see what happens. So first we move the negation across the first universal quantifier to obtain this proposition, and then we keep moving the negation forward and across the second quantifier to get this proposition, which is logically equivalent to the negation of this one. So this proposition is false whenever this one is true. And this one is true whenever there exists a pair xy that makes this proposition true. In other words, there is a pair xy that makes P false. And that's exactly what we ended up with intuitively. So this is just a way of checking that we're doing these things in a correct way. Now, even when considering only two universal quantifiers, there's still another way to make this predicate here into a proposition, namely by switching the order of the quantifiers. So I want you to stop the video and to convince yourself that this proposition is true exactly under the same conditions as the first one, and this proposition is also false exactly under the same condition as this one. In other words, these two propositions are logically equivalent. Now, another way to build a proposition out of the binary predicate P is to first use a universal quantifier and then an existential quantifier for x and y respectively. And the proposition we get is for all x there exists a y such that Pxy. So what are the truth conditions for this proposition? Well, this proposition is true if for every x, every possible value of x, it is possible to find a value of y that makes P of xy true. Remember, you read these quantifiers from the left. For all x, there exists a y such that P of xy. Now, under what conditions is this proposition false? Well, again, one way to do it is to consider the negation of this proposition and then to move the negation past the quantifier. So what you get is there exists an x such that for all y, not P of xy. In other words, the negation of this proposition is true or this proposition is false when there exists at least one value of x for which p of xy is false for every y in the domain. Now I'm going a little bit fast here, so it's your job to stop the video and make sure to process this information as deeply as you can. Once you've done that, let's consider the next possible way of building a proposition, namely to first use an existential quantifier and then a universal quantifier for x and y respectively. Now this proposition is true when, as it says, as you read from left to right, one can find at least one value of x such that p of xy is true for every possible value of y. There exists an x such that for all y, p is true. And similarly, this proposition is false when its negation is true. And its negation says, for all x, there exists a y such that not p of xy. In other words, this proposition is false whenever, for every possible x, it's possible to find a y that makes p of xy false. So far, we have used two universal quantifiers in the two possible orders, and then we've mixed and matched the quantifiers also in two possible orders. So the next consideration is when we use two existential quantifiers together. There exists x, there exists y, such that p of xy. This proposition is true intuitively when there exists at least one pair of values for x and y that makes p of xy true. And it's false whenever p of xy is false for every pair of values for x and y. Now, I want you to consider what happens when we switch the order of the existential quantifiers to get this proposition. Please stop the video and determine the truth conditions for this new proposition. Okay, welcome back. I hope that you came to the conclusion that these two propositions have exactly the same truth conditions. In other words, they are logically equivalent. So the conclusion of this analysis is that sometimes the order of the quantifiers matters, and sometimes it doesn't in nested quantifier situations. In particular, one conclusion is that the order of the quantifiers only matters when what? Well, notice, for example, here that when we swap the order of the for all and there exist quantifiers, we obtain two different sets of truth conditions. So in this case, the order definitely mattered. On the other hand, in this case, when we swap the order of the universal quantifiers, and in that case, when we swap the order of the existential quantifiers, in each case we ended up with logically equivalent propositions. So in conclusion, the order of the quantifiers does not matter when the quantifiers that are nested are the same, either both universal or both existential. The order of the quantifiers only matters when you are nesting different types of quantifiers together. Now, another thing to notice from this analysis is an interesting symmetry in these truth conditions. For example, if we start with the proposition with all universal quantifier and move to the proposition with all existential quantifiers, we notice that the truth conditions are flipped. This indicates a fact that is called the duality between those two quantifiers. We say that one quantifier is the dual of the other. In fact, a same or similar situation happens when we mix and match the quantifiers, and we switch the order of the quantifiers that are nested we also observe a flipping of the truth conditions. Now, to conclude this segment, I hope that this rather lengthy analysis of the truth conditions of nested quantifiers helped you develop a deeper understanding of what it means to nest quantifiers, and also realize that you have to be careful when you nest quantifiers to use the appropriate order, the one that reflects the meaning you intend to convey.